So I'm teaching biomechanics of human locomotion. I know it's biophysics, but biomechanics are pretty close relative of that. And this is sports biomechanics that we usually work in our Locomotor performance lab. We built the lab 2 years ago. If you guys want to visit the lab, that's like a mile from TCU on Westbury Street. So you can visit the lab. What we usually do is usually running science, jumping performance science, and we are doing bunch of other stuff there right now. So, and I have a bachelor's in physics, so I transferred to doing biomechanics. So if you guys ever want to transfer that, that's a good region to start researching in. So lab directors, we have Dr. Peter Weyand and Dr. Emily Haig. So we have two departments, which is kinesiology, applied health sciences combined at the lab. This is our lab team. You have Sunil Prajapati, who is a lab engineer, then me, second year PhD student. Parker, who is a Olympian swimmer. He was a captain of the swim team. And then Dom, just first year master's student, who just joined the lab this year. So a little bit about me. Like I said, I'm a second year PhD student. I'm a research assistant at the lab. I have a bachelor's in physics. I have two masters. One is in kinesiology. Second one is in exercise physiology. So that's how I combine physics and biology together to be able to do my PhD. I also coached track and field in college, and I also ran 100 meters. So what I'm researching right now is like a fantasy line, close to fantasy line for me. And you'll see why when I show you the videos that we go through. So the agenda for today, I'm going to tell you what is locomotion for humans, like how we use physics for locomotion. And then I'm going to tell you some of the concepts that we use in locomotion. Then I'm going to tell you about the research that has gone through in the past 3 decades. And then what's next in biomechanics. At any point when we jump sections, I'll stop for you to ask questions. So make sure I like to make it interactive, not just me talking and you guys listening. That's boring for me. So what is locomotion for humans? So starting, we have Isaac Newton. So this is where majority of the things start for biomechanics with Isaac Newton. We're still using, after 400 years, we're still using 3 laws of Newton. As you know, the first law, that you have to apply external force for an object to move, or an object will keep on moving, or if you don't have an external force applied to it. Okay, so first law. Second law, F equals ma. So Dr. Hannah told me you guys are really good with Newton's law, so I'm not going to go too deep into those. Okay. Third law, action reaction. So since you guys are really good at those, I'm not going to go too deep into it. So this is where the motion picture started that you guys see today. Okay, the motion picture started with movement science. Okay, I'll tell you why. So there was a bet in 1872 with Leland Stanford, who co-founded Stanford University. So the bet was, when the horse runs, because horse racing was really popular, when the horse runs, if the hooves of the horses are in the air at any time, a point when the horse runs. Okay, that was the bet. His friend was saying, horse is always on the ground, it never goes into the air. Okay, so they hired a photographer called Edward Muybridge. What he did was he set up 24 cameras and a tripwire. So whenever the horse passes, it trips the wire, takes a picture, and then they'll be able to figure it out. So which is, if you have your regular camera right now, it at least has 30 frames per second. So that's 24 frames per second that he was able to enact there using 24 cameras. So who won the bet? What do you think? What do you think? Does horse go in the air ever? Yes. It does. Okay. Well, at that time, it was not really apparent for people if it goes in there. So that was kind of a video he came up with. So you can see at some point in time, horse goes in the air, right? Which is, since horse runs really fast, people couldn't be able to figure it out at that time. So that's where the two things divided, where motion picture media people took it over this as building motion pictures, and Muybridge took it to study movement science. So he took it to do running performance, jumping performance, throwing performances. So he went a different direction than what the motion picture were trying to do. I hope you appreciate that those are pretty cool pictures, right, from 200 years ago. So in the 1900s, the scientists who pioneered, took the movement science forward, which was Warren T. Inman. He was a surgeon, orthopedic surgeon, who studied in human gait science and everything. So he has really good books and research out there. After that came Dr. Rich Taylor. Now he has really extensive research in animal mechanics at Harvard. He is my advisor, Dr. Weyand's advisor. So he's my great grand advisor uh, from Harvard, and that's Dr. Weyand. So Dr. Richard Taylor did a lot of research with animals, and Dr. Weyand took it forward to do research with like top athletes, like sprinters. And there's a so this is the lab at Harvard that Dr. Wayne worked at for 10 years. As you can see, it was a 62-acre land that Harvard had, and they had all kinds of animals there. So all the pictures you see are from the lab. So that's the lab that they had out there. So they'll put the animals on the treadmills and try to find their gait patterns. So you can see a kangaroo. That on the right side, you can see Dr. Wayne doing the VO2 max on there. So that was the lab. I have a video for you guys about that.
For an animal to increase speed, there are basically two ways it can do it. One is it can take longer steps or more steps per minute. What animals actually do is sort of a compromise, particularly within a run or a trot. Most of the increase comes from taking longer strides, and it simply spends more time in the air and less on the ground to go faster.
What is it you're trying to find out by running animals on the treadmill?
One of the most interesting things is that we found that all animals use their muscles and tendons as springs when they run.
When an animal hits the ground, it stores the energy of impact in its legs, and it uses this energy to help push off the ground on its next stride.
So that was his lab. Let me stop that. There's top. Can I stop it? Can I stop it? Can I stop it? Should have. Okay, let me just do that because I don't want to go to the next before I talk about that. So while watching that, you saw a lot of animals run on the treadmill, and they're able to find this. We still have a same kind of treadmill at the lab right now, which goes 90 miles per hour. Uh, so by looking at those were really early research into animal biomechanics, using different kind of animal models and equations to find out how animals run, which also goes into evolutionary biology, how animals evolve. So we will also talk about like size principle that go into biomechanics and how physics affects life, the evolution overall. Any questions about that video? That's how that was pretty cool, right? When I first saw it, I was mind blown with that video. So that's from Harvard. The lab's not there. Now here we are after learning about animals is the running science. So that's the treadmill I talked to you about. So this is a Nike study. We collaborated with Nike on this project. We're still collaborating with Nike on shoe mechanics and shoe performance. So we are able to do this testing, top speed testing, then the endurance testing on the treadmill. Uh, So this is top speed testing. As you can see, athletes are able to run on 12 mil. Yeah, that's really fast. I think that's about 28 miles per hour. The person's running. That's Dr. Wayne back there testing the athlete. So what does that give us? So the treadmill that we have, that's a force embedded treadmill down there. So we get forces from the treadmill. So that's where physics comes in. We get forces, and as you can see, we also have on this particular person, we don't have markers, but we get something like this. So as you can see, we also do motion capture on them, so we can get their limb mechanics, the kinematics, and then the force place that we have in the treadmill gives us the kinetics. So you can see on the graph, what you have is a vertical force being applied by the athlete, and then the dark line, you can see that's the horizontal force. So as you can see, the vertical force is the peak vertical force is 5 times their body weight, which is about 1,000 pounds. So the person is applying about 5 times his body weight to be able to run that fast, which is pretty awesome. At that, we'll go into more concept about how we do research using that data set, but that's usually what we usually get. That's the primarily things we get from it, which is the vertical force, horizontal forces, and the time metrics. As you can see on there, there's an airtime, again, the same as the horses, right? It also has the airtime. There, are we gonna see how airtime is manipulated by athletes, or even if it is manipulated by athletes, to be able to run faster. And then we also have the acceleration science, acceleration mechanics there, which is different than the top speed. As you can see now, that's a dual force plate system. The top line that you can see, the top graph that you can see, that's the front pedal that's pushing, which keeps on pushing for longer. And then the bottom one is the back pedal. So as you can see, there's different kind of forces being applied during those. So this usually gives the coaches really insight into how to manipulate the skills and mechanics of the athletes when they run. Okay, before we go into concepts, was that cool? Right? That's pretty cool. See, I told you this is a fantasy land for somebody like me who did track and also coach track. So to be able to do research like this is pretty awesome. So concepts, now this will be fantasy land for you, since we all talk about equations into that goes into the testing. So coming back to Newtonian mechanics, that we have the basic principle, the second law that we have is force equals mass into acceleration, which we break it down into velocity and time, and then it breaks it down into impulse momentum equation. So impulse equals momentum usually. We usually primarily use impulse a lot into the research that we do, which transfers the impulse momentum. Like I said, the impulse momentum is pretty important, which transfers into the research, is the mechanical work in terrestrial locomotion. Like I said, back in the 1970s and 80s, there's a lot of research was going on with animal sciences and the energy expenditure realm. So what they found out is the primarily mechanical requirements of locomotion. So what is required for you to walk, run, do any kind of activity. So they were able to find out that the amount of forces you need to be able to just walk equals 1 times body weight. So you need to apply action reaction. You need to apply equal amount of force to the ground to be able to just stand. So if I'm standing right now, that means my body is exerting equal amount of force as per my body. If I'm not capable enough, I'm gonna fall. I won't be able to walk. I won't be able to do anything with that. That's force. That's where force comes in, and the time comes in. So time is how long I'm applying the contact force for. So if I'm walking, I'm simply walking. That just basically means my speed is determined by how much force I'm putting into the ground and how much time I'm spending onto the ground. Okay, if I don't spend enough time, if I don't spend enough amount of force into the ground, what's gonna happen? I'm gonna fall, right? I'm gonna fall. So that's why it's important to those two metrics are really important to have, but we still break them down into more metrics to find out really how they interact with each other. So like I said, walking is pretty simple. You walk like you are using a stick. So you just move across the stick. There is a pendulum kind of a thing happening with walking in order to pendulum. But with running, it's like a bouncing ball. You're bouncing because you have airtime, right? So with running, it's kind of different. Like you come down, you act like a spring, and then you go up in the air. You come down again, you act like a spring. So it's like a bouncing ball, which leads us to bring up a new variable, which is length of contact length, LC. So LC is basically horizontal distance you go when you move, when you run or anything. So if I'm contacting, first contact, and then if I go in the air, so that horizontal distance you have is the contact length. Okay, questions about that? Cool, pretty easy stuff. So how does LC manipulate it? So usually LC is constant across speeds, but what changes is the contact time. As you can see, I have a graph. As speed increases, your contact time is decreasing. So we just talked about force and time, right? So common sense, it makes sense like, oh, if I need to apply more force, I need to increase time, right? That makes sense. But the contact's reducing there, right? Which is opposite of what normally we would think. Is to increase force, you need to increase time, but the contact time is reducing there. And as speed increases, the contact times goes to almost like 0.10, like tenth of a second down there, and they're still able to apply that much of a force, which is 5 times body weight. So contact time must decrease as speed increases. And why is that? We will talk about that when we go deep into the research. So as we know, force needs to increase, contact time needs to decrease. So this is a general relationship. When you increase speed, they spend less and less time on the ground. As you know about impulse, you need to be able to have that much speed, you need to have higher impulse, right? Impulse momentum relationship. So impulse momentum is force times change in time, right? So if force increases, your time is decreasing, right? That what's happening to impulse at that moment?
It's staying if the coefficient of that staying relatively constant.
Yes, perfect. Yeah, it's staying relatively constant. So this is true for level ground sprinting, constant level ground sprinting. So this is true for level ground sprinting. So impulse stays the same. When you go up, go down, which leads us to the next thing. So as you can see in the video, I just have this video so you can like visualize how everything's happening over that. So as you can see, we have contact time there, and then the air time, and the peak forces over there. So there's a double peak you see as soon as they land. There's a double peak. So the first peak you see is the braking force. They have to brake, and then apply force and move on forward. Okay. So going deeper into the science of it, the speed equation. So Dr. Weyand, in his 2000 and 2011 papers, he came up with a speed equation. So what is speed equation? So we just talked about impulse, so up impulse. So what is up impulse? So when you're running, when you're coming down, you need to push yourself up, right, to be able to hold that weight, hold that much weight during the contact time. So that's basically impulse, F average times TC. So TC is contact time, how much force you're applying onto the ground, and average force is the amount of force that you're applying during the whole stride cycle. Then you have the impulse down. So what is impulse down? So gravity is always working on you during the whole full stride cycle, right? So gravity is pulling you down. That gives you the impulse, which is your body weight. So gravity is putting you down with a force of body weight. And then the T step is just time of the total step. So gravity is acting over you for the total step. The up impulse is just this, when I'm touching down and getting up in the air. But the down impulse, which is the gravity acting upon you, is when I touch down and go all the way to the next step. So during the air time is also the impulse working on me. Okay. Questions? Okay, so based on what we talked about, this impulse is going to stay constant overall. So that impulse stays constant. That means up impulse equals down impulse. Does that make sense? Pretty common, right? So if up impulse is down impulse, what that gives us average force equals impulse divided by contact time, right? Which gives us this relationship, which is if you take the average force divided by body weight, so that gives you mass specific force for every person, each person. Because if you say you have a 200-pound guy and you have a 150-pound guy, you're gonna say, oh, 200-pound guy is gonna apply more force. That's why we normalize it with body weight, which equals the ratio of the step time to contact time. So the ratio of your mass specific body weight is equals to your step time to contact time. That's a main principle of what we do research in. Questions? Okay, cool. That was easy. I thought that you guys were probably gonna have questions about that. Which leads to our speed equation. So speed, usually we know speed equals distance upon time. So we have distance, which is for running, which is the step length, right? How far we went with one step, that's step length. But time is the frequency of steps, how fast we're moving our steps. So speed in running is step length multiplied by frequency of steps. Okay, and those two of them are so when you increase step length, your frequency goes down. When you increase frequency, your step length goes down. Okay, so those are interrelated. What we do with that is, as we talked about, L step to LC ratio, which is equals to T step to TC. So the step length ratio to the contact length is equal to the step time to contact time ratio, which also we talked about is equals to F average to body weight. Does that make sense? I went too fast there, considering you understood everything. Yeah, go ahead. Question?
I'm following.
Okay. Don't worry about it. I like to interact with people. So considering that ratio, what we took out is the step length, which is L step, equals to LC, which is the contact length times F average divided by body weight there. Okay, so this gives us LC. So LC is pretty important for running the contact length. And then the forces, how much body specific forces you're applying to the ground, which determines your step length. Following? Good till here? Okay. That gives us one metric. We broke down step, what determines step length. So these are the two metrics that determine step length. Going into the frequency of step. What is frequency of step? So what is step time? Step times is basically contact time and air time, right? So we just divided 1 divided by Tc plus T here, okay? That gives us frequency of steps. Now plugging these two things into the equation, which gives us the speed equation, right, for running, which is basically mass specific force times LC, contact length, times 1 divided by Tc plus T here. Makes sense? So this is a revolutionary speed equation Dr. Weyand came up with in his 2000 paper, and we break it down even more as we go through the research. Cool. All right, and that's Michael Scott running the 31 miles per hour, which is not humanly possible, but he's still doing that. I have a picture for you to visualize, but you guys understood everything I said, which is good for me. Yeah, yeah, good.
I'm just trying to get like a grasp of some of the intuition of this, because
Yeah.
Like I imagine that some of these variables are like deeply connected. So for example, if you have a bigger average force, you're probably going to be in the air for longer. You're having a bigger acceleration.
Yeah.
Up in the air for longer. You're probably also going to have like a bigger step size.
Mm-hmm.
So, I had a question on that. I forgot it. I'll come back to it.
Go. You go it.
Yeah, I think mine is just also. Then this just comes in, I guess, why, in general, like you would find that people who are taller or like bigger foot size would then have a little bit of an advantage when it comes to running. And
yes.
Yeah.
They do. So that's why we have the speed equation, right? Yes. So if they're tall, they're gonna have naturally taller LC, right? They're gonna have natural tall LC, but their frequency is gonna suffer, right? They're not gonna have like a faster frequency there. So that's where they suffer over there. So we did research on like body sizes of athletes. Same question we asked is, if being tall helps you run faster, why not every sprinter is tall out there? So we have a size for sprinters from all the way from 1.65 meters to 1.96 meters. Mm-hmm. And usually they fall between like 6 feet tall, which is like a sweet spot for sprinters. So that because of this equation, there is like a plateau.
All of it that comes together, like it's not just the.
It is true that if you just like drop them to like a constant treadmill speed, they'll be faster. But there's another component, which is acceleration. They're going to be really bad at acceleration because it's going to take them a longer time, because larger mass, they're going to have larger mass, longer limbs. And as if you can see, even think like having longer limbs is really not that good for sporting performances, because then you are not able to lift as much weight as per your body weight. Like we have seen research in Olympic lifters. Higher you go in body mass and size, lower the percentage of weight you lift, because longer limbs, as you can know, our body is structured with a third class livers. So the longer limbs means larger torque you're gonna have, right? So the muscles will not be able to produce that much force. So it's really hard for taller people to produce as much force, which is shorter people are able to do that. And muscle size, we found out, is muscle size, like the length and size, like volume principles are different. So as you go up in size, you don't the volume doesn't go up in size that much. Volume lags behind. Like the 3D principle of that. And there's like a size principle, like there's a limit to how much you can enlarge your muscles too. So really being tall, because when I came to the PhD program, I was like, I went through this, and I told Dr. N, it's just gonna be taller people running faster. And he's like, just go through a few more years and you'll learn why it's not the case. So yeah, good question. Yeah, good.
You have to look at what angle the force is being applied because if someone
Yes.
goes straight down.
Yeah. For constant speed running, like top speed running, it's kind of makes sense that they're applying, like they're coming down at like a underneath their body center of mass, because as you can see, like the video, as you can see, try to go back. Let's see. Okay, so in that video, as you can see, the majority of the force they're applying is the vertical force. So to be able to apply vertical force, you need to go down vertically, right? If you go at an angle, then you won't be able to. There is a little bit of horizontal force that you can see there, but not a lot. Like you can see horizontal force is like even lesser than the body weight that they have.
That's the small.
That's a small one, yeah. The small one right that down there, that's the horizontal force. So like I said, reset. But as you can see right here is where they break. That's why you have a negative horizontal force. So they're coming down at an angle. So that's breaking backwards, so that horizontal force backwards. And then they slowly, as they move with the step, they're slowly moving forward. And this is where the angle comes in and they propel forward with that. But that's not the most important intuition here. Like I said, they have to apply a large amount of vertical force. So they have to, like, when the contact, so as you can see, when he comes down here, it's like right there. So it's like the angle of force application is about like 89, 87 degrees overall. So it's not a lot. Where it matters is for acceleration. When they get out of block, that's where it matters a lot for acceleration, like force application patterns there.
So does that mean that, like, physics, back to baby physics 1, is that majority of the propulsion is due to friction? Because if you're not having much horizontal force,
Mm-hmm.
then the only way to get horizontal movement from the
Yes.
vertical force is if there's a friction.
You have to understand this at, like, for sprinting at top speed, they have already propelled themselves to top speed, so they're coming out of the blocks. So they have already done everything that they need to go to propel themselves in horizontal direction. So it's like, think about it, that's why it's like a bouncing ball kind of thing. So you already like push the ball, so it already has all the horizontal velocity you need to give it, and then it's gonna go forward. Now what happens with the ball when you drop the ball is it slowly goes down and down and down and down. Why it's doing that? Because it's not applying enough force for it to just keep in that perpetual motion forward, which happens with them too, that they just run out of kind of a neuromuscular energy at the end, and then they deplete. I'll show you like velocity graphs, and you'll see how they like go up and then slowly go down, taper off. But yeah, so they have made majority of the horizontal velocity they need to make. The only thing they need to do at top speed is just carry their weight.
Right.
You just need to stay upright.
Okay.
Cool. It's a little intuitive. Dr. Wayne has spent 3 decades in this, so. Okay, so that's the speed equation, as you know. So we break it down even more to, like I said, body size. So this is where body size comes in. Like, it's really important. What happened? Okay, it's really important to talk about body size here because it does affect how you run at top speed. It is true. It is an advantage. But like I said, an elephant and a mouse are gonna use different metric, like running mechanics, running gait patterns there, right? It's intuitive. Now the question here is, do elephants run? Yes. Who says yes? Okay, 4 people, and all of you, yes, they run.
Wait,
Okay.
what is the definition? Like, I think if we're coming, like, there has to be airtime with running enough. I don't know.
Yes, there is airtime with running. That's what constitutes running. No, but they do reach the top speed of 35 miles per hour.
Walking really, really fast. That just speed walking.
Right. Okay. Right. Okay. Cool. Right. They're applying a lot of force. So considering them being like about 3-4 tons, it's really it takes a long time. Like they're like nature's amazing gift, or I don't know. It just being that big is really hard. for any animal. So yes, they cannot run. Do giraffes run, or do longer animals are able to run?
Yeah.
Do they? So you saw a kangaroo run, right? What's the basic principle that they run? Like what do they use?
They jump. They have the spring.
Galloping, yes. So springy legs, yeah. So the energy is stored in their tendons of the legs, and then they're able to accelerate forward, right? So that's the size principle that we have. I basically wanted to touch on those. Okay, before we move on, questions? Any more questions about the concepts of running? You have chances to ask. So going down into research now. So Dr. Weyand, like I said, 2,000 study, they're able to find out now for coaches, track coaches, or any normal human. If you want to run faster, what would you tell them to do? What would be the first basic instinct you would have? If you have two people and one is slower, what would you tell the other person to do to be able to run faster?
Yeah.
Okay, now you know it's push harder. Yeah. Maybe, but it's just okay. Move your arms faster. Say that again. Longer strides, yes. What else? What else? But think. Okay, step frequency. So move legs faster, right? So that's kind of a basic intuition. Is we see it in cartoon, right? Oh, whoever moves faster is able to speed up faster and go faster, right? That's what coaches used to coach back in the day. It's just like move your legs faster, move your arms faster, you're able to run faster. Okay, so Dr. Wayne went and did research. Does it really matter how you move your legs or reposition your limbs in that? So this is a study. This is a really famous study back from 2000, still till people still use it, get cited in the research. What he did was they used three kind of metrics. They use decline running, incline running, and irregular running. Okay, so they're able to like change their gait patterns over those. There was over 33 runners, so they use like different kind of runners, so slow, intermediate, fast. So there's runners all the way going up to 6 meters per second to 11 meters per second. So they got like a big range of runners there. So what he is trying to do here is to find out if leg repositioning matters or the force matters or something else matters overall while people are running, right? The basic intuition is you need to move your legs faster. So these were the tests that he did with people at top speed. So the top speed steps, it's 8 steps. They only did 8 steps because, like I said, usually when humans run at top speed, if you see like a 100-meter race for Olympics, usually they can maintain the top speed for only 8 steps. It's not possible. Like it's really hard for. They don't fatigue. We just recently found out. Like coaches used to think, oh, we just fatigue. So what do we need to do? We just need to run more so we can increase the endurance. But they don't really fatigue. Like they still have a lot of fuel inside their body to be able to run. But what's happening there is we are not able to send signals as fast as possible after a certain time. Our neural links fatigue after some time. So that's kind of a new research into that. So 8 step is our limit. Like that's how long we are able to maintain top speed, at least for 100 meters, and then they slowly taper off after that. So this is the result from the research. So I'm gonna give you a minute to see like if you could see. So what you have on the top is the swing times, and what you have in the bottom is the forces, the body weight normalized forces. So just look through that, kind of try to have your own conclusions and see what you can figure out from that. It's just one athlete. It's an example across speed. So on the x-axis you have speed. So speed going from 3 meters all the way to 10 meters per second. Okay. What can you tell me about the swing time? So swing time, the definition of swing time is touchdown. This leg is in the air, and then going all the way to forward. Okay, so that's swing time for the one leg. So coming down, touchdown, all the way till I touch down for the next step. So that's the whole swing time. So step time. That's the step time that we talked about. Okay, the swing time is a step time. Aerial time, we talked about it when the person is in the air. Contact time is the person is in contact with the ground, and then we have force and impulse. Okay.
Well, the force is, at least on the ground, the force is going up with speed, but pretty linearly. So if you want to increase speed, the force you get to increase force proportionally. The impulse is going down though, which means that the time in the air is going down faster than force is going up. If that makes sense.
Okay. Okay. Good intuition. Anyone else want to make a conclusion? Yeah. Go ahead.
Let's say aerial time doesn't really matter. It's pretty much a flat line.
Okay. Perfect. Okay. Air time doesn't matter. Like I said, swing time is like total step time, so that comprises of aerial time plus contact time, right? Both of those. So what you have swing time, as you can see, swing time up there, that's aerial time plus contact time. So does the contact time and the swing time matches as it declines? Right? It kind of declines with the stem. So the majority of the swing time decrease that you see is because of the contact time decrease. Right? So contact is decreasing. Well, what's the best intuition that's happening right here? Force is increasing, right?
Yeah.
It's increasing largely as you go up with the speed, right? So limb repositioning is given by your air time, which is not changing that much, right? So that brings us back to our result is when force increases, speed increases. It's a basic, simple relationship. And that's when coaches started applying more of a cues as to run like you're hitting the nail with your foot or run like you're like stomping the ground. Before they used to teach coach like, oh, just run like a gazelle, just run like light. When you get to top speed, now coaches are telling them to like stomp your foot as fast as possible on the ground, okay, as hard as possible, so you're able to maintain that and apply more forces. Make sense? Okay, so that's the first research that Dr. Weyand did. Then Dr. Weyand did a second research. Now we know basically right now is force matters, okay? So we took care of like one part of the equation, but in that research we also figured out TC is going down. So what's happening with TC there, okay? So in this research you kind of figured out what's happening with TC, and do we have a limit? So you would say, if I'm applying more force than the other person, will I be able to run faster? So that's the kind of question they ask. Am I able to decrease the TC over time? So right now we know you need to increase force, decrease TC. Well, what is the limit of that? There has to be a limit, right? Humans always have a limit. So in this research, we try to find out the limit of that. So the way he did this is, last time, as we know, he did incline running, decline running, and constant speed running. In this, he did one leg hopping, backward running, and forward running. So one leg hopping, he did that to figure out if you're able to apply more force onto the ground, right? Backward running to be able to figure out if we can manipulate contact time within that, okay? Because there's a different gait patterns you use in the backward running, and then there's regular forward running. So one leg hopping. Now again, I'm gonna give you a minute to go through the graphs. What you have on the top is the F average, and what you have all of them are F averages, but it's six different people there. So what do you think is happening over there? Think about it. This one is the forward running. This one is one leg hopping. This one is the forward running. So what's happening over there? Force and speed. So x-axis is the speed. Speed is increasing, and force on the y.
I feel like if you are only applying one leg at a time, or one leg as opposed to two legs, you're kind of going to scale half as fast as if you were applying both legs. So it seems like it's going in a similar direction, but it's not reaching as far into the speed with these same or higher amount of force.
Think about it. When you run, you only apply force with one leg too. When you run.
Frequency of those
Okay, so right now, what you're saying is since they're running with one leg hopping, their contact time may be increasing. Since you're talking about frequency,
I would say more like wouldn't their step time be increasing? Because if you once you leave this one, normally you have your next foot coming down right
yeah.
afterwards. Instead, you have to then wait until that foot
Mhm.
reaches again, and during that time, you're not being able to apply any force.
Right. So
And so
more airtime.
Yeah.
More airtime. So because you're saying because they're in the air more, they're applying more force into the
They're
ground.
applying more force on their kicks, but it's not actually resulting in quite as much speed as both legs.
Okay. Okay. Yeah. Good.
It looks like they're not using all the force they can use. Like look at graph D. It looks like they're able to go up to 3 newtons.
3 body weight, like body weight times. So 3 times body weight. Yeah.
3 times your body weight, but when you're running with 2 legs, you only get about 2.5 times your body weight.
So they are able. Each leg is able to produce a higher. Individually, legs are able to produce
They
a
are
higher.
able to use that somehow when they're running.
Okay, they are, but so what you see here is a thing called force reserve. So they are able to apply more force, but they're not. So there's something happening there which is not able like they're not able to apply that amount of force there. They are capable of applying force, which what we try to find out is it possible for humanly possible for us to apply more force into the ground? Yes, it is true they're going into the air, or their frequency is uh, reducing, is longer. They're But the whole goal of this was to find out, are they able to apply more force with one leg? Yeah.
Do you know if they tracked like vertical height during this same study? Because like I feel like if you're one leg bouncing, you're gonna need a higher vertical during those strides, and I feel like that can also result in the more ability to apply force.
Center of mass tracking. So what happens with that is impulse up, impulse down. So that same thing also happens here. So amount of impulse you're putting right here, that's the amount of impulse you're gonna also see. So center of mass, if you're applying only vertical force only vertical force at top speed, like they're doing right there, there's not gonna be a lot of center of mass repositioning. So displacement of center of mass, that's what we're trying. So if they're coming down here, they can go as high as possible. When they come down, they're gonna be at the same center of mass, like height of center of mass, right? So there's like a net zero center of mass change over there. So they can go as high as possible. Usually for which is my research right now to track the center of mass or top speed, they usually don't go more than 5 centimeters when they're running at top speed. But for this, as you know, like impulse up, impulse down. So what's happening here is they are applying more force onto the ground, but they probably would be spending a lot of time on the ground to be able to do that. But we separated contact time or the air time, other metrics. The only thing we were looking at here was the force. Is it physically possible to implement more force onto the ground? Because after a certain time, you won't be able to. Because like I said, all locomotion is capturing the elastic energy that you're producing, like the action reaction, and then be able to implement that into your speed, like apply that forward. Yeah.
So this brings us back to the question of does one leg hopping engage different muscle groups than running? Because I don't like in my eyes if they use different mechanisms, it's
Yeah.
not fair to compare the forces that they produce and say, oh, you can produce more force when you're running if it is a different mechanism for hopping altogether.
Think about it again about running. It's basically you're hopping.
Okay.
Even in running, you're hopping, right? Because it is a ball. It is the same kind of ball. But what we are taking out here is we are just taking out, oh, you cannot land on this next step with the same foot.
Yeah.
All you can do is just keep landing on the same foot. So running is equivalent to hopping. The only thing differentiates between one leg hopping and like actual running is air time. There's gonna be reduced air time.
But it is the same muscles and everything.
Same muscles, yeah. It's gonna be the same muscles because basically to be able to flex your knee, to be able to extend your ankle, to be able to extend your hips, you're gonna use the basic same muscle principles. And we think more on the mechanical terms for the human body, like how the forces are acting and how we're able to apply those forces back onto the ground.
Yeah.
So we consider that human body as a one full functional unit. There are scientists who do muscle mechanics, like, oh, if there are different muscles working, but the hypothesis here was, is force being applied more using, but it's relatively the same activity, considering that. Make sense? Question?
What about balance though? Because like if you're one leg hopping to provide like an artificial balance, because it's asymmetrical movement, whereas with running you've got symmetrical.
That is a really interesting question, and I'll tell you a secret. The paper is being published right now on that. Usain Bolt is asymmetric. Okay, so his one foot is half-inch taller than the other foot, and the researcher Sunil, Dr. Prajapati, he did research on that. He put insoles in the shoes of the runners to find out asymmetry helps top speed running, and it does. It does help top speed running. Yeah, so pretty intuitive. Yeah, go ahead.
Not about asymmetric leg, but what if they have a dominant leg,
Mhm.
dominant arm? So does this study account for maybe they're using their dominant leg versus their not dominant leg?
For one leg hopping, they only use dominant. Like we asked them to use dominant for them.
You push them, and whichever leg they fall on. That's what they do for snowboarding and skiing. You push them, and you'll always fall. Well, instinctively you fall on your dominant leg.
Or we basically also tell, like, kick a ball. Like you'll always kick a ball with your dominant leg too. So because dominant leg is usually faster. Like my dominance is right. It's usually faster than like a left leg. But if you tell me to jump, I'll jump on my left leg. So it gives me more stability, and I'll be able to move my dominant leg. Okay, but yeah, they use dominant leg. Intuition here was, are they able to apply more force, and they are able to. So that's what we call the force reserve there. Yeah.
Sorry, just going back on like the asymmetry with that is, what is the like principle behind the fact that you have asymmetry actually makes you run faster? Like, what is it?
Okay, think about it. Like I just told you, like taller people are really good at top running, but where they get down is the frequency of steps. So
Yes.
having maybe a little bit imbalanced leg asymmetry, they're able to apply forces which are like one leg will be providing like higher force, one leg will be providing lower force, but the other leg would be going faster, like frequency wise, will provide more frequency. There's all kinds of intuitions into that, having imbalances. So if you are on your longer foot and you're in the air, so if the other foot is not as symmetric as the other one, as you're going down a longer distance, right? So that increases the velocity of your foot that's going down. So the braking force, which we figured out, so the two peaks you saw in that running, the vertical two peaks, the first peak was the braking force, right? The second peak was the propulsive, like they use the press onto the ground to propel themselves forward. We figured out whoever has the highest braking force is the fastest runner. So the stiffer you are on the braking, the faster you'll be able to go, because you absorb a lot of force into that and you're able to transfer that force forward. But if you're really good at complying, you're not going to be really good at fast top sprinting, because action reaction, again, you need to be able to take all the force that ground's giving all up to you. So that's another intuition, is that being asymmetric might be able to manipulate. You're able to get best of both worlds, having those two kind of things.
Is there then almost like, when you're just thinking of training, for example, if my right leg was longer than my left leg, would you need to be stronger in your left leg than in your right leg, because the left leg is coming down at like at the higher force and applying the greater force?
That's a really good question.
Or wouldn't that necessarily like?
It's no, that's a really good see, and this is why he did that study is because coaches when they go or any physical therapist, they're like, oh, asymmetry is bad for you, right? They're like, of course we would think asymmetry is really bad because if you think an asymmetric person leg, they're gonna wobble, right? They're gonna be like keep wobbling like this. So this is basically bad. So what they try to do is strength and conditioning coaches. They try to coach. They try to train where athletes are not asymmetric. So they try to do like lots of unilateral exercises, so like one leg squatting or any unilateral exercises, so athletes don't have asymmetry into their limbs. They'll try for that. So what you're asking is, does the other leg needs to be stronger than the one leg? They do try for that. And the asymmetry study that we did, we're like, keep them asymmetric, keep them asymmetric. They'll be able to run faster. But those differences only show up at top speed. Like other like they're gonna be limping probably. It's a half inch difference maybe probably, so it's not a big thing. But yeah, keep them disabled so they can run faster. Yeah.
Just like I'm not too good at running, so I don't know. But I mean, it sounds like if you want to keep your legs stiffer during impact, and then stomp more, right? That's a lot more pressure. That's not like gonna add more strain on the legs themselves, right? Because I mean, I at least know like running on concrete that puts more strain on your ankles.
Yeah, it does.
But I'm wondering if like will this also like put more strain on the muscle groups, or is it relatively fine?
Yeah. As you can see, even one leg hopping or regular running, they're applying about 2 times their body weight. So it does put, and that's average. This is average force. Peak forces go 5 times body weight. So it does put a lot of pressure on their legs. So you see marathon runners, their shoes is like thick as like this, just to be compliant with that force. But for these people, for top runners, they want to increase that force as much as possible. To be able to do that, what they have is their longer tendons, which is not scientifically proved, but they do have longer tendons, like longer Achilles tendon. So to be able to have a longer tendon, they are able to store that elastic energy into it and then apply back onto the ground. So they do that, but that is required for them to be able to run fast. Is they need to have that kind of force into it. And now they have top speed, like they have sprinting shoes with carbon plates too, which helps them even more storing that elastic energy and force into that to be for them to be able to run fast. Yeah.
So I'm guessing just like relatively in the past 100, 200 years, I think like evolutionary, we as people haven't really gotten faster. We just been able to understand the physics behind it better so that people can run faster.
I like this class. This is you guys are smart. Yes, that is true. Yes. Dr. Weyand has said this on like a video. He gets invited to like YouTube videos about running and limits of human locomotion. He has said that there too. Jesse Owens back in the 1930s ran 10.3, and the current record is 9.58. That's basically because we have better running track, because he ran on a dirt track with like regular spike shoes. Like they have shoes with nails in it so they can have a grip on the dirt track. Now we have like a super sophisticated synthetic track, rubber track, and then we have shoes and everything. So yes, I would say all of the changes you can see in sprinting science is because of mostly because of, I don't want to discredit the coaches or us, the scientists who study the biomechanics, but majorly it's because of being able to have better equipments. Yeah.
Are these tests mainly run on professional runners or recreational runners, or like not runners at all?
This is a combination. This study was a combination. Like usually, first 2 studies he has done in 2000 and 2010. This is like a wide variety of it because they wanted to make sure it applies to general population and not just get down to just elite runners, which I am doing. I'm just focusing on elite runners, which will be third study. So okay, moving on. So that's the force reserve. Next graph is comparing backward running and forward running. So again, take a minute, think about what's happening over here.
Were they also run at the same speed? Like, try to maintain the same speed?
Yeah, so speed increases. As you can see, each dot here is like at different speeds. As speeds are increasing. This one is the let me see. Sorry. Yeah, this one is the backward running, and this one is the forward running, right there. What do you think happening with both of them?
I think very much the same.
There's near similar TC minimum. Yeah. There is a slight difference in the what is it? Is this the time on the y-axis?
Yeah.
Yeah, time on the it's in seconds.
Then you get it. So
So
inconclusivity.
we ended the test when they reach top speed, so they're not able to go any more than that. So that's their top speed for that.
It looks like they're a little bit more efficient with running backwards because you can get the same speed but using less contact time, which means you can apply more force.
They haven't reached the same speed. As you can see right here, the running backwards is this 6 meters per second versus 9 meter. At a given they are, but again, think about it. They probably won't be applying as much force, which is required there, right? The intuition behind this is, as you can see, running backward top speed versus running forward top speed, they end at kind of the same contact time. So does that tell you like maybe contact time is the real limit to top speed? Like they're not able to go more than that. Like there is no way they can go under 0.1 second on the contact time.
Because if it was, you'd see a difference between speeds. Contact time was if the contact time was the same, but you have a different speed, then it's redundant.
There's different speeds, different activities there. The only difference, like the only thing that's the same for both of them is all of them has kind of a same. You can see that's the TC minimum. You see that? Imagine what's the contact time. What are you doing during the contact time? You're applying force, right? To be able to apply force, what do you need? Like I said, why do athletes fatigue after 8 steps?
You need to engage muscles. You need to
right?
do all those pathways.
Right? So that's why this minimum exists for them. It's not possible for them to have even lesser contact time that they could. That's their like physical limit of the contact time, right? They're not able to apply because if you walk, the minimum amount of force you need to apply on the ground is your body weight, right? That's the basic we talked about, is the body weight. At that speed, you need to apply more and more and more forces. Keep applying more forces, or he said we're gonna fall, right? You're gonna fall if you don't keep up with the force. You're gonna fall. So to be able to maintain that force, this is the minimum contact time you'll be able to apply. So that's the TC minimum they found out. The first study we figured out, you increase force, your speed's gonna increase. This study we find out you are able to increase more force, but why are you not able to? Because of contact time, right? You can't increase contact time more because force increases, contact time has to go down, right? So there's a force limit. You can't increase more force because contact time is not going down anymore over that, right? Because impulse has to stay constant, right? So those two things needs to go up and down. Make sense? Oh. Okay, so limit to running speed is primarily limited time needed to apply. Limit to running speed is primarily time needed to apply the force. Don't worry about that, but we're limited. I think that's an extra word. But it is limited by the time. Okay? Force, you can apply more force, but you cannot reduce more time into that, right? Makes sense? That's study 2, study 3. This is my study now. We use a 48 national, international caliber sprinters here. So no general population involved in here. Speed range 10.5 meters per second to 12.26 meters per second. That is really fast. That's 22 miles per hour to 28 miles per hour over there. So those are fast people who ran on the track and the treadmill. We did I didn't, but the researchers did 2-step minimum, so 2-step averages. They took like a high-speed video of their steps, so for us to get like their TC, TR, which was the metrics for us. So what we found out, look, now remember, like first study, we figured out you need to apply more force. Second study we figured out is TC doesn't go, like there's a limit to TC, so you cannot increase force. So as you can see in this F average, straight line. Everyone is applying equal amount of force. So at elite top speed running, you would be thinking, oh, whoever applies more force runs fastest. That's not the case. Everyone's applying equal forces. Frequency, you say, oh, you need to move your legs faster. Frequency, straight line. There's nothing there. Okay. What's different is the LC. Okay. So the length, contact length, is slightly increasing. That is the only significant metric that you can find that explains why people are faster. As speed increases, LC increases over that, right? The contact length increases. So that is true. Taller people are going to be faster because of their LC, right? But if you do it over the whole 100 meters, this doesn't show up because of acceleration mechanics. So that's also my study. So top speed, what matters is the LC. This is what determines who's going to win. Makes sense? So that's my research there. So first research, we figured out force increases, speed increases. Then we figured out the limit to speed is due to contact time. And my research is increasing TC increases speed. Okay, 3 research. That's about research. That's it. I'm not going to talk too much about research now. This is my current research, which is 9-second 100-meter possible. Right now, the record is 9.58 seconds. Is 9-second possible? So what we use is a bi-exponential equation for that from Henry from 1954. I'm not going to go too deep into that, but 2 metrics that we study here is the K1, which is the acceleration constant, a constant that they're able to accelerate, and K2 is the deceleration constant that you can see. So from here to top speed is their acceleration constant, and from here to all the way to when their end is their deceleration constant. So how did they decelerate with that? And we also use Dr. Weyand's speed equation to be able to help with that. So what we did was on the y-axis you have the velocity, x-axis you have time. So that's the velocity profile for Usain Bolt's 9.58. As you can see how his velocity is increasing, it goes up, it goes a little bit down, then this Morris Green, and then Marion Jones, and then that's the predicted sprinter. So that's the trajectory needs to be for a predicted sprinter to be able to run a 9-second 100-meter. And for him, he needs to reach 13 meters per second speed. Right now, the current top limit is 12.26, which is Usain Bolt. But the person who will be able to run 9-second, he needs to run at 13 meters per second for top speed. So we are still doing research onto that. Like, what would be the limit? Is it possible? Dr. Wynn thinks it's not possible, but more shoe technology, equipment, we might be able to. They didn't think back in like 1980s 10 seconds is possible, but there's like 1,000 people running 10 seconds. There's high school kids in the backyard running 10 seconds right now in Texas. So anything's possible. But this is research, my research that I'm doing. And then, like I said, acceleration is another fantastic way to study sprinting science, because it takes like about 30% of the race acceleration zone. So that's acceleration right there. One of our past PhD students doing acceleration right there, and we get graphs like this. That's a horizontal velocity, which is important. So for acceleration, both, as you know, for top speed, only vertical is important. But for acceleration, horizontal now is like 50% or more than that of that part, because the majority role of acceleration is the propulsive forces that you're applying onto the ground. So the hypothesis we make for our research in acceleration is first is the propulsive force, which is horizontal force, is going to be higher. However, if you are able to accelerate better than me, you're going to have a higher propulsive force. And how are you able to know that? So the dark blue is a slower 5-meter run, and the top one is the faster. So as you can see, basically, he's able to apply more horizontal force, and that's why he's faster, or 5 meters. Okay, basic principle. And then he slowly applies, gets up, slowly gets up. Now he's in the lean position, slowly gets up, 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 and gets all the way straight up. And that's when he is at top speed. Okay, and we talked about top speed. Another intuition here is the TC. TC is going to be lower. Whoever has the lowest TC, again, for acceleration too. Now we might think, oh, higher TC is going to help acceleration because they need more time to push on the ground, but lower TC will be better for acceleration. Now, if you can think about this, I have given you the blue is the acceleration, and orange is the top speed, high velocity, and these are LC LOs. Okay, so LC, we have the contact length divided by the leg length. Okay, so that gives you like a ratio of, takes out the height principle. So if you're taller, that basically levels the field if I divide it by the leg length. Okay, so as you can see, this is the acceleration. We only have 2 steps for that. Actually, this is top speed, and this is acceleration right here. So as you can see, for acceleration, LCLO is lower, right? So shorter contact lengths for them, which gives us what?
Bigger force.
Think about it a little bit more. Contact length is lower for them, short contact length. They're not moving as much forward as they would at top speed. It is longer than top speed. Uh, that's what tells you it is longer than top speed overall. But even though in that you see a lot of variation, right? You see that the top speed is like a kind of a in that bubble, but you can see that acceleration is all over the place. So we are hypothesizing that you can accelerate different ways. There's not a one single way you can accelerate. But top speed, there's one way. You have to follow that pattern. You have to follow physics. But acceleration is more. You can use different metrics to be able to run. You can manipulate TC. You can manipulate T air over there. But overall, you need to have like a lower TC in that. And the last one is the T air. T air, again, different T airs. This is a T air for a high velocity. As you can see up top here, it's like bunched together. Here you can see variation, a lot of variation into T air. So different ways to accelerate than top speed. Okay, what's next into biomechanics research? Amputee athletes, right? Amputee research. Dr. Weyand were able to do research on Oscar Pistorius, 2011. He came to the lab to run, and World Athletics was saying he has unfair advantage to be able to have those kind of curve-shaped legs and have a full carbon fiber into it. And he able to figure out that he is having advantage over that leg, but the Europeans said no, they're not, so they let him run in the Olympics. Don't quote me on this. I'm gonna get in trouble though. But yes, so we do amputee research into that. Next is exoskeletons. Again, getting outside the body, doing exoskeletons. If anyone's interested in working in exos, come talk to me. I want to work in exos as much as I could. That's like a really, really, I like exos. If I could work on them. And the third part is the robotics. As you can see, that's the Boston Dynamics robot that's going 28.3 miles per hour. So 3 different things we can apply biomechanics. See, in robotics, I figured out is like the limit of robotics is the energy it requires to be able to do that. and which gives me a deep appreciation of what as humans we can do. Like we are so efficient at, like, we are not the fastest animals on the planet, but we can outrun anyone, every animal on the planet. We can outrun them all, and that's why we are here. We are the most efficient animals.
Yeah, we're really good marathon runners, but not
EG is higher than a car. If you drink a gallon of Pepsi, you'll run far further than a gallon of gas.
That's crazy.
Wait, sorry, say that again.
Just calories. If you have a bottle of Pepsi, 1 gallon of Pepsi, it'll take longer to burn that than it does for a car.
Yes, that's true. Yeah, that's why I said it's. I just appreciate us as human beings is how efficient we are. It just shows up as, like, I don't know, 3 million years of evolution in ourselves. Like how the choices we have made over the past billion years is how we have gotten into this today. So talk about robots taking over. Well, unless we find out a good energy source for them, or physics goes into quantum physics, like if you guys do research something like that, maybe they will. But right now, the constraint is the energy for that, and even for exosuits. So that's physics.
What is
That was it.
Sorry.
Go ahead.
Actually,
Go ahead.
for the exoskeletons, what is that? I actually don't know a lot about that. What is that mostly used for? Like
Military, yes, military or workers in the factory. Okay, to be able to make them more efficient, to be able to like lift stuff or do things all over that, because our stuff is better to, humans are cheaper sometimes than machines, but they're still weaker than machines. So you give them a little bit of boost so they can function better. So that's where exos come for, or military, of course, to be able to kill each other.
Nice.
Yeah.
Is there more research into what exoskeletons?
There's a lot of research.
Like used for, except military and construction? Is there?
You can use it for.
Or
Yes.
the power armor from Fallout.
Yeah. Well, on the nicer side, exos are used for rehab for Parkinson's patients, or paralyzed people, or like people with injury. So they can get into the exosuit and walk. So it trains their gait patterns to be able to walk. And then, as you know, you need to train the muscles to be able to build them up. So if you want to walk again, you need to walk, but you won't be able to apply that much force, right? If you're like, if you have any kind of disease or disability, you're not able to, the only requirement is for you to be apply more force. So what exos does is just helps you half the way to be able to apply that force, or just keeps you up. So at least you're doing the half the work, and then you slowly reduce the help, and then they're able to walk after some time. So I have a really great example, since you guys like Marvel. Do you know when what's the Tony Stark's friend's name, the military guy? Yeah, the Patriot. You know, he falls down from the sky when Vision hits him, and so the new no, he's not the new Captain America.
It's in Civil War.
Yeah, with the War Machine. Yeah, so he falls down. At the end of the movie, you see him in exoskeleton. Like he's not able to walk around. He's paralyzed, so he's walking in exoskeleton. So that's another thing you could do for injured people. Cool. Yeah.
I know you said you primarily work with top athletes and such, but can you like discuss like what the field looks like, for instance, for like physical therapy offices, things like that? What kind of research is being done for like people who maybe have medical conditions and that their biomechanics may be
it's
impaired?
think about this is what we're doing in our lab is trying to figure out the absolute human limits, like what we're able to do. Now, if somebody is not able to apply enough force onto the ground, are we able to manipulate other metrics? Are we able to manipulate maybe longer contact time? So that's what they do with like prosthetics. They have a longer contact time for them. So since they're not able to apply more like force, so they give them like a curved leg. So they're like rolling on that foot. So they're applying like longer contact time. because they're not able to apply enough force because they don't have a tendon, right? I mean, the curve shape gives them like an elastic recoil, but it still like doesn't give them a lot of help with that. Yeah, go ahead.
Do you think doing all this research on running has made you a faster runner? You practice it.
Yes, I do run. It's you still need a coach. You still even if you know you need a third eye perspective of what you're doing and all of that. It's hard, and what they're doing, top athletes, there's like a bit genetic component to that too. But yes, to be able to see the research and being a sprinter, I'm gonna run. I'm gonna run this year in a meet. I'm gonna run 100 meters and I still coach. So it does help me to be able to see all the research, and which keeps me excited about it because I get to research and go and try it out there, which is fun. It's just fun for me, or just be a bookworm and just research and read through it. So, which I believe that's why you also guys excited in physics, right? You're able to do cool stuff. If you guys ever want to come by to the lab and see like a testing, you're welcome to, and you can ask more questions. We have a lab that with 14 motion capture cameras and a 5-meter force plate runway. So 7 force plates, which are about $20,000 each. 14 motion capture cameras. One of them is $7,000, and the treadmill is $100,000 by itself. So we have a really cool lab. It used to be an old Blockbuster, which closed, which closed down. So we call it we call it a Frogbuster. Well, yeah, thank you guys. Questions? You want to come by to lab? Let me know. I will give him. He has my email. If you want to just come by to lab. Interested in research? You can switch like I did. I did my bachelor's in physics, and now I'm a biomechanist. So, want to do something cool? You can switch.
Nice.
Thank you. Appreciate it.